So there are a bunch of things that we are going to do regarding multi-layer neural networks. Uh, but depending on how soon the patents that Google and Facebook are filing come through, we may have much less to do because I can't teach patented stuff. I have to pay them something. So batch norm, which I would like to talk about, has been patented. Dropout, which I'd like to talk about, has been patented. So this is a new era that we are living in. Poor Dijkstra didn't know that he could patent Dijkstra's algorithm. And right. Turing certainly didn't know that he could sell his machines everywhere. And so now, on the other hand, Larry and Sergey and Mark have figured out a way of selling anything. Interesting stuff that these basically, there's a lot of researchers in these companies now, and they get to patent the stuff that they do. You can do it too, but in general, that's not a particularly nice thing for science. We will worry about that later. But before we go forward, are there any questions? Yes?
So you're not allowed to even discuss if it's patented, or is it just knowledge learning?
No, I'm just kidding, of course, but at some point of time we'll get to that. No, obviously you can do whatever the heck you want. You're a university, nobody cares about you, in general. Because they realize that you have no money and you won't make any money, so it's okay. It's only when you try to do a startup and you try to use batch norm, you may have to send a couple of dollars to these guys. I don't know if you guys know, for example, Java was patented by Sun Microsystems. And it's not that they were after you because you use Java, they just were after Google because it used Java. Because that's like deep-pocketed company. So this is sort of trade wars, I guess. Most of the Facebook algorithms cannot any longer use, packages cannot any longer use batch norm. And then of course, probably Jan LeCun will say, I sold my soul as well as ConvNets to Facebook, and so you can't use it anywhere else, and so Google can't use ConvNets, and that'll be fun. But we will worry about that later. Yes, it's exactly a joke. This stuff we can talk about. It is true, however, that they have been patented, and you haven't been talking much about patented stuff in your classes, I'm assuming. That's something to keep in mind. Okay, any other questions? Okay, so quick review. Perceptrons can be used for linear regression or binary classification, which basically using logistic regression. If the classes are linearly separable, this will work. And the logistic regression is nothing but perceptron with sigmoid activation or threshold function. By the way, the word, I've been using the word threshold function. But people also use activation function. So essentially, the inputs are coming, you weighted some of the inputs, you pass through the G, which is your nonlinear function, and that is either called thresholding function from the old days of gating or activation function. Okay, and then so if in fact the classes are linearly separable, you can separate them using perceptrons and logistic regression. And basically, logistic regression is nothing but perceptron with sigmoid function as a threshold or activation function, and cross entropy loss as the loss function. There are many different loss functions you can use, one of which happens to be cross entropy loss. The other happens to be the mean squared loss that we talked about most of the time. I actually didn't show you the gradient update equations for the cross entropy loss. I just showed you how the loss looks like. Probably at some point of time, I will send you a worked out example of how to derive the updates for the cross entropy loss function. There are even other kinds of losses. For example, support vector machines use these things called hinge loss functions. And basically, you get to define error any which way you want, and then you try to minimize the error using gradient descent, right? So anyway, that's about the perceptrons. And the single layer perceptrons can be used to learn multi-class concepts. We talked about, remember, you can stack up in the same layer. You can have multiple perceptrons, one for each class. So perceptron 1 tries to say, is this class 1 or not? Perceptrons 2 tries to tell you, is it class 2 or not? Is this class 3 or not? And there are 15 classes, so you have 15 perceptrons. Okay, and so in fact that's a very useful problem. So for example, I might want to develop such a perceptron to decide whether it should be grade A, grade B, grade C, grade D, grade E for the people in the class, instead of just saying pass or fail, right? So it's a multi-class classification problem. Okay, but then we talked about the fact that perceptrons cannot learn classes that are not linearly separable. And of course, this is not surprising because if you just look at the equation of that perceptron, all it is saying is, in some weighted sum of the inputs, greater or less than somewhere. And so that would be a definition of a hyperplane. So if the points are on one side of the hyperplane, then it will say yes. Another side of the hyperplane, it will say no. Okay, so that's what perceptrons are basically trying to do. So they cannot learn classes that are not linearly separable. So the question, of course, then is what classes are not linearly separable? Are given an arbitrary training data, can you tell right away whether or not it is almost linearly separable? It turns out that the easiest way is to run a perceptron on the data and check if it gives you zero error on the test data. Do you understand what I'm saying? So in fact, the simplest way to check whether data is linearly separable is to run the perceptron. And if its loss function, training loss in particular, goes to zero, okay, test loss also goes to zero, then basically the perceptron has converged. And so that's actually the way to compute the linear separability, because you don't get to see multi-dimensional data in a nice little picture in front of you, except that one guy who used to be there who said he could see 4-dimensional apples. Most of you can't. And so you actually run perceptrons, and that's basically to see whether it will converge or not. And in fact, if you, for small examples, the thing that we looked at last class was the Boolean function examples. For the Boolean function, 2-input Boolean functions that we have looked at last class. Let's see where it is. It here? No, it's not. It's okay. So the 2-input Boolean function examples that we looked at last class, we saw that XOR function basically winds up having, in 2 dimensions, XOR function looks like this in 2 dimensions. This is plus, this is plus, this is minus, this is minus. And there is no way of drawing a line that separates the pluses from minuses. So this is a simple example that tells you, if in fact one of the nice things in general in proving anything is to prove that the theorem is true is much harder than prove that the theorem is false. Because to say that the theorem is false, you need to provide one counter example. If you can come up with one counter example, you have proved that you've shown that the theorem is false, right? And so if the theorem is perceptrons can learn all functions, which is what Frank Rosenblatt in effect was thinking, Minsky and Papert just has to show, hey guy, here is XOR, and you're done. Okay? So that's basically what we looked at last time, and then of course you can learn concepts that are not linearly separable by using either of 2 ideas. One is blowing up the dimensionality first. So if you have 2-dimensional data like x1, x2, then you basically increase its dimensionality to infinite dimensions, up to infinite dimensions. There are many different ways of blowing up the dimensionality. One might, for example, be like say x1, x2, x1 squared, x2 squared, x1, x2, x1 cube, x2 cube, etc. All these are all terms too. So now the 2-point data point has now become a many coordinate data point. Okay? And then if you do that, then you can see if in this bigger space, is it linearly separable. And actually it turns out that any data is linearly separable if you increase the dimensionality sufficiently. Do you see what I'm saying? Okay? This is actually connected to the idea that we just talked about at the end of last class, which is that any function can be approximated with just one hidden layer. You thought those are two, you might think that those are 2 different ideas, but they're basically the same idea. In fact, the hidden layer can be thought of as telling you the blown up dimensions. Do you see what I'm saying? It's the same idea in two different ways. And as I said, in fact, historically, these ideas sort of interleaved. First was the neural networks, then came the blowing up dimensionality stuff. Well, it was actually done around 60s too, but it only became widely available, widely known in 90s onwards. And then you had support vector machines, yes. And then you came to, back to neural networks. Yes, please, go ahead.
Is dimensionality always sufficient?
What?
Dimensionality is always sufficient for linear separated.
Separability.
Yeah.
Yes, yeah.
There's the increasing dimension. You get to the point where it's linear separable. Because
Beyond that, there's no point. So you can just basically, in fact, the best you can do in classifying a binary class, okay, whenever we are talking about learning, most of the time, the simplest problem we'll be thinking in terms of is binary class classification problem. Even though the multi-class classification problem can also be done by anything that can do binary class, okay? So pass-fail classification problem, okay? For that, all I need is, put a line between the passes and fails. And above the line is passes, below the line fails. That's it. Okay? The interesting thing is there exists some way of blowing up the dimensionality such that in this new bigger space, data is always linearly separate. Okay? That theorem happens to be called Mercer's theorem. And that is just as useless or useful as the other theorem that I talked about at the end of last class, which I'm going to take again, which is for a neural network with one hidden layer. So if given any continuous function, any arbitrary continuous function, there exists some neural network with a single hidden layer that will be able to approximate this function to any degree of accuracy you want. These are connected, and the more you realize that they are connected, the better off you are compared to people who think deep learning is the only thing. You see what I'm saying? They're all connected ideas. Okay. So then multi-layer neural networks, and the other idea, of course, is the multi-layer neural networks. And as we pointed out, multi-layer neural networks basically involve perceptrons being stacked into layers. Yes, sir. Being stacked into layers. It's extremely important to understand that the only way you say multi-layer is if one perceptron's output becomes the input to the other perceptron. When you had the multi-class perceptron, they were all getting the inputs from the input layer. And their output is just going out as the output of the overall problem. Do you see what I'm saying? There was no internal nodes. Nodes which basically whose outputs go to somebody else as inputs. That's the important thing. Multi-layer basically means there exist layers, okay? And if you just have one hidden layer, you already have full expressiveness in terms of continuous functions. And if you have more than one hidden layer, if you have two hidden layers, then you have full expressiveness in terms of discontinuous functions too. And are there any other functions in the world? There are continuous, there are discontinuous, that's it. Do you see what I'm saying? And by the way, these theorems are very similar to the kind of, Archimedes' lever theorem, which is, they say there exists such a network. Finding such a network may not be easy. Which is kind of the connection between the kinds of questions people are asking on the piazza as to, if you can do fine with just one layer, or two layers at the maximum, what the heck is the point in having 250 layers? What? What?
Not blowing the dimensions much.
No, they are blowing the dimensions. They're basically blowing the dimensions, and so basically they are computing features in terms of other features. Every layer can be thought of as new features, new dimensions. Okay? Basically they are computing dimensions in terms of other dimensions, and it turns out, we will talk about this deep depth property multiple times, but it turns out that there are some training advantages in terms of computing deeper networks. But it is also possible that actually people very quickly might find out that in fact you will be able to find the right network, the right single layer network. The problem with this part of the lectures is this is the part that you're most interested in hearing because you're hearing about deep learning everywhere. But this is the part that's not really an undergraduate level subject because it hasn't stabilized. I basically did not go to my lab today. I sat at home changing things that I taught 2 years back. Okay, because already even at that 471 level, things that I said last time are no longer necessarily true because people have figured out that they were not true. Do you understand what I'm saying? So it's fun times to be, this is like you are at the frontier. Okay, it could be good, it could be bad. Frontier means you have lots and lots of jobs and your boss also knows nothing. You never know anything, but you certainly don't know. But frontier also means, basically you may well be doing something wrong, because you're using yesterday's results as against today's results. Okay? Now, in particular, I actually mentioned on Piazza that there's a significant amount of work that's going on right now about infinitely wide networks. Infinitely wide basically is essentially single hidden layer, but it's infinitely wide. If you just read this, and this is actually, they are coming up right now, this work is being done. I think I actually gave a link to Sanjeev Arora's paper, who's doing very good work in theoretical directions on neural networks right now. And it turns out that you have a way of understanding, not fully, but at least you have an entry into that direction because infinitely wide is essentially like kernel trick. In fact, if you read the paper, it basically, even at the abstract level, they'll say, oh, we will use tangent kernels. The kernels are the way you actually blow up the dimensionality. So you can have dual interpretations of the neural network. You can see it as doing the kernels, or you can see it as doing the neural network. And if this is not enough, a little while later we will talk about probability and Bayesian networks, and we will start talking about another interpretation of neural networks, which is really the most important one, which is probabilistic interpretation. And in fact, if you take a normal machine learning class, you should be taught about probabilistic reasoning and Bayes networks first before you touch neural networks. Okay? Anyway, so that's one other part. So one thing that I want you to understand is, remember at the beginning actually the sigmoid network, the perceptron networks essentially can have an activation function. You could have perceptron networks have linear activation functions too. But if you have perceptrons having linear activation functions and you have stacked them into layers, what would happen? It would still be a linear function. Do you see what I'm saying? A function of, if you have inputs and you take a linear function of the inputs, then you take another linear function of those inputs and those results and the linear function of those results. What you get in the end is still a big old linear function. It's still a line. So expressiveness can't be there if you only consider linear functions. There should be some non-linearity, which is why we always talk about things like sigmoid function, or the step function, or the hypertangent function, any of these functions, hypertangent function, etc. Okay? So that's kind of an obvious thing, but you should remember that you must use nonlinear thresholds. Otherwise, it makes no sense. So without nonlinear threshold functions, the stacked layers of perceptrons is just equivalent to a linear perceptron layer. And then these are the two theorems we just talked about. Theorem 1, continuous function can be approximated by some neural network with one hidden layer. The hidden layer may be arbitrarily wide. This is the infinitely wide neural networks. When people talk about infinities, it's not that they'll ask the computer, malloc infinite amount of space, right? It is just that the theory does not care about how wide, how big the input is going to be. Okay, so in this particular case, the infinitely wide networks are connected to the kernel trick, which we won't talk too much about, but it is useful to make that connection. The other theorem is any discontinuous function can be approximated by some neural network with just two hidden layers. Okay, and we talked about this part too. that essentially you have these kinds of networks. This is a perceptron network. This is a multi-layer network where essentially two perceptron units, their outputs are going into this guy. That's why it's multi-layer. Okay. Now, currently when you talk about neural networks, you essentially have many such layers, maybe 250 such layers. Okay. And so that's the part about it being deep. But the depth actually doesn't buy you anything in terms of expressiveness. It currently feels as if it is buying you something in terms of learning efficiency. But this is a moving target. Right now, in the exam, if somebody asks you, in your interviews, somebody asks you, you can say, well, depth seems to help in the learning rate. And in fact, some ideas, such as batch norm that we'll be talking about, when connected with the deep networks, make it easier somewhat to train them. Okay, but part of it is really nobody tried to find infinitely wide multi-layer networks and train them yet. That's also true. So this is the only thing that's working. So for example, this is why this part of the AI is really engineering. Okay, when you built one first arbitrary looking bridge, you didn't check, is this the optimal bridge to build? You look at those Roman bridges, they look funny. You know, they look like nice things that you can make posters out of. The new bridges don't look at all like that. They're much better bridges. They look very different shapes and very different ways of holding the bridge, cantilevering the bridge, etc. The first bridges that were built, at least we have a bridge. Let's be happy. You see what I'm saying? While there are some engineers in some theory people sitting in some room saying, let's look for the optimal bridge before building one. In which case, all these people will be falling into the water. Okay? So this is where we are. This stuff works. But that doesn't mean this is the only thing that works. And as much as you want to get your job, I want you to understand that things will change in your lifetime. Probably next week. But at least in your lifetime. Okay. So in terms of multi-layer, the one other thing that we won't talk about, but it's worth mentioning at this point, is both these kinds of networks. As I said, the only thing that's common between the neural networks and brain is the word neural, right? Because they have neurons and they have N-E-U-R is the only thing that's common. Because brain has neurons and neural networks have neural. Okay, that's about the only thing that's common. Everything else is a very high-level analogies. In particular, one of the things is the connections in the brain. While neurons are connected to each other in the brain, those connections are bidirectional oftentimes. They're not unidirectional. Which is why, if I were to give you, let's say you heard like a whole song, right? And you remembered the name. Which basically you heard the song and said this is the name. Okay, so if next time I give you the song, you will remember the name. If you trained a neural network to take the Shazam, for example, and then take the song, tell me the name, it will tell you. But now you put the name of the song and the output, it says, I don't know what to do. Do you see what I'm saying? Everything flows one direction. You give me the song, I'll tell you the song name. If you wanted me to give from the song names, I should give the song, there should be something else. I can't do it. But your brain does both. This is basically what we call associative memory. First of all, I learn entire things. Okay, and if I then, basically in some sense, I learned the song, as well as the name of the song, as well as who was I hanging out the first time I heard the song, as well as how good was the bread that I ate on that particular day. All these things are connected. And how many of you have brought, I'm sure many of you have basically heard a song and suddenly remembered some incident from the, back in the past. You are not neural networks. You are not feed-forward neural networks. That's what I'm saying. So if you never did, then you probably are feed-forward neural networks. Okay, yes?
Is it possible to build bidirectional?
Yes, that's what these are. And a large amount of time between 1960s and 80s, while they couldn't do anything with these they were doing also work on bidirectional networks. In fact, there are great names for these, like Hopfield network, Boltzmann network, and restricted Boltzmann network, etc. And most people who got into neural networks and hang around for a long enough time really wanted to finally crack these. And as I don't know if and I probably didn't mention it here, but there was a course on deep neural networks that Jeff Hinton taught on Coursera in 2013. It's no longer available on Coursera because they removed it, because it's completely dated, in the sense what people are using is not what was in that course, okay? But it's actually available on his webpage. And that course essentially still talks about what he was hoping will work. What he was hoping will work would be some combination of feed-forward networks and bidirectional networks. He would have this idea of stacked Boltzmann machines with an AND feed-forward. And the interesting reason why he was even considering it is when we get to things like Bayes networks, which we will hope to live and get to. Bayes networks are essentially a representation of probabilistic distribution. They look very similar to neural networks. They will be like, nodes and connected to other nodes, connected to other nodes. And there are arrows, except their semantics are completely different. It's basically, this is a representation, it turns out, of a probability distribution. We'll talk about it more generally later. But the point is, there, if you tell me what is true here, I'll be able to tell you what is the distribution of any of these nodes. If I tell you what is true here and here, I can tell you the distribution of these nodes. Probabilistic networks are essentially bidirectional. Okay? Because distribution has no direction. And so in fact, his idea at that time was to train feed-forward networks by viewing a large feed-forward network, for example, as a Bayes network, and use probabilistic network learning techniques. One particular one we'll talk about is expectation maximization. And then run it for a little bit, and then do feed-forward network stuff. The reason was normal feed-forward network wasn't working. Even as he was teaching this course, engineering developments made it so that, in fact, normal feed-forward networks already are easy to train, so you don't need this. That doesn't mean these are never needed. They are not needed for this. If you want to understand actually how brain works, you better understand this stuff. And in general, these are what are called generative models. And these are all discriminative models. So these guys only learn the connection between, if you give me the inputs, I'll tell you the outputs. Because in essence, the probability terms, they learned just this. PO given I. Conditional probability. Okay? Whereas these guys learn POI, joint distribution. And those of you who might still remember probability might remember that PAB is PA given B times PB. R PB given A times PA. So essentially, if somebody was learning this and somebody else is only learning the middle part, so somebody is learning PAB and you only learn PA given B, you learned less than those other guys. Do you understand what I'm saying? The guy who learned PAB can do what you're doing plus more, because you will only be able to figure out the distribution of A given B if you learn PAB. Whereas that guy can do PAB, PBA, PA and B, PARB, anything. That's what generative models are. Basically, probability distributions are generative models. And you can think of what neural networks are trying to do in essence as basically learning this discriminative model, P, output given inputs. In the best case, I would have done the probability first and then done this. But then I won't have you. Because you say, my God, the end of the semester is coming, there's no deep learning, I'm sick of it, I'm tired of it, I'll go somewhere else. So we're giving you the deep network and we'll keep you hopefully, and then I'll tell you what actually is the background that you need to understand why deep learning works. Okay? Okay, so that's basically bidirectional models, and that's worthwhile keeping up, but mostly there's not too much work going on the neural network side on this part. Okay? Okay, so and then we were talking about multi-layer networks last time, and we talked about the fact that in fact for multi-layer networks too, you can essentially compute the weight update rules. Just the same way, using the same chain rule. And in particular, I pointed out that there is a whole entire history. In fact, if you do that, basically one question, of course, is when psychologists were doing this, they were worried about, okay, at the output layer, I know what the error is. I know what is supposed to be the output. I know what the network said is the output. And so I know the error, so I can use the error to change the weights. But how am I supposed to know what is the error at the interior nodes? I don't know what they're supposed to be. This is stuff you made up. In general, in neural networks, there's only two objective truths. The inputs and the outputs. Everything in between you just made up. And so you don't know what their values are supposed to be. But you want to be able to make them up in the right way such that given new inputs, you will be able to correctly get the right outputs. You see what I'm saying, right? Okay, so basically people were very worried about even touching this problem for the longest time because they didn't know what the heck is going to happen about the error here. And actually for a while, in fact, the way to pacify psychologists was to say, well, you can think of this error 100 and then you can spread it around to every one of these guys because these 4 guys are connected to the top guy. If the top guy has error 100, these guys have somehow contributed to having that error 100. So we will essentially kind of apportion the error to each of these in proportion to the weight with which they are currently connected to the top guy. It makes sense, sort of intuitive sense. You didn't know whether it really made any theoretical sense or not, but it makes intuitive sense, right? And in particular, as I showed, in fact, if one of the weights is 0, then this guy has no error because whatever this guy is doing, it is not contributing to the error that you saw. Right? But it turns out that you don't need to do that psychology, that sort of a pre-mathematical reasoning. In fact, you could just do the chain rule based computation of errors, the gradients, okay, layer by layer. Okay, and that's basically what I was